Speaker is Ramanujam. He's a professor here in IMSC who works in theoretical computer science, and he's going to talk about elections.
Good afternoon. Am I audible? Can you hear me? I didn't hear a yes or no, so. Am I audible there? Can you hear me? Can you hear me there? Okay. Yeah. So the title has slightly changed from what I had put out in the abstract out there as is our leader really our leader, and so on, right? So as Ananta said, it's about voting systems, elections, and so on. But maybe before that, something on, yeah, okay, so thanks to Sushmita and Varuni, and do feel free to interrupt with questions anytime, and don't wait for the end if you want to ask something. Okay, so this thing is about generally selecting between alternatives. You want to make a choice between a set of alternatives, maybe which laptop to buy. Okay, it could be factors like price, how cool it's cooled, what somebody thinks about it, etc., etc. Could be whatever be the reasons. Now, one way to think about it is that you have some preference over all the laptops available in the market. If you say there are 10 of them, you have some preference ordering over these. So think of it as a relation, a binary relation on this set. And it's kind of reasonable to expect that if you are a rational person, your preferences are transitive. Transitive means what? That if you, let me see if I can find this. Yeah. So if you prefer Mac over Acer and Acer over Lenovo, it's kind of reasonable that to expect that you would prefer Mac over Lenovo. So this is the property of a transitive relation. If X is preferred over Y and Y is preferred over Z, X should be preferred over Z. Now, usually preference is not total. That this relation is an ordering, it's a transitive ordering, but it's not a total ordering in general. That means you would have alternatives which are incomparable. It's not that I prefer one over the other, right? So that's common. But I'm going to, for the purpose of this talk, I'm going to only talk about total preference relations. So that means that you have a transitive relation, and between any two, you clearly prefer one over the other. I know it's unreasonable, but just bear with me. It just makes life simple, easy for us to think about. Now, what is really interesting for the purpose of this talk is not individual preferences, but somehow to derive group preferences. Suppose I know individual preferences for several individuals, how can I derive group preferences? Suppose there is a group of 5 friends on the same laptops, each has some preference, and each is a total transitive relation. Can we somehow infer what the group prefers? As a group, as a team of 5, what you prefer? Now, clearly, if everyone in the group, all 5 prefer a Mac over Lenovo, it's very easy to say that the group as a whole prefers Mac over Lenovo. That's easy. What about 3 prefer Acer over Lenovo and 2 prefer the other way? What can you say about group preference? What would you say? Because it's 3 as opposed to 2? Yeah? It's a numerical majority, right? Therefore, that's okay, that's one rule. Question is, this majority rule is probably the most prevalent rule in our society. For many things, we use majority. So the general rule is that infer that a group prefers A over B if a majority in the group prefer A over B. This is the rule, and we commonly use it. Now, if each of the preference relations that's given is a total relation, then it's not very difficult to see that the majority relation is total as well. Because If you take the majority, okay, you can sit and figure it out. What about transitivity? Supposing you got a transitive relation for each of the individuals, what about the majority rule? What gives given? Is that transitive? Well, let's consider three people. I'll write it as a vector, as a sequence, A, B, C, to mean that person 1 prefers A over B over C. Person 2 prefers B over C over A, and person 3 prefers C over A over B, right? These are the three vectors given. It's very easy to see that a majority prefer A over B. Can you see that? Because person 1 prefers A over B, and person 3 prefers A over B. So the majority prefers A over B, and a majority prefers B over C, because both 1 and 2 prefer B over C. So majority prefers A over B, majority prefers B over C. By transitivity, you would think that majority should prefer A over C, but that is not the case. C over A. So the majority rule is not transitive. Is this clear? Is what I'm saying clear? Should I go over it once? 2 out of 3 prefer A over B, 2 out of 3 prefer B over C, but then you would expect majority to prefer A over C, but that is not the case. 2 out of 3, in fact, prefer C over A. So the majority rule is not transitive. Okay, big deal. Why should you worry? Right? But I'm just saying it is true. Huh? So question is, what are the kind of, for individuals, we said, okay, my preference should be transitive. If I'm a kind of rational kind of person, if I prefer A over B and I prefer B over C, I should prefer A over C. So if this is your basis for thinking that this is a rational way to make choices, why should you admit something irrational about the group choices, right? Group preferences, there must be some rationality that you want, right? So what are the kind of properties that you would like? We fixed on total. As I said, total is not really required. It's just for purposes of giving a talk that is easy, right? If it is partial orders, then there's a lot of painful stuff to manipulate for not very nice to do for a talk. You need, with pen and paper, you can do a lot. But there's no problem. But transitivity is something more about the way we think. And okay, so there are two options at this point to say that, hey, majority rule is important for me, I don't care about transitivity. Another way is to say, but transitivity is important because I do attach importance to it at the level of individuals. What about some other rules instead of majority? Is it clear what I'm saying? Any questions? So what kind of rules that you might think of? If not majority, what rule would you employ to infer group preference from individual preferences? You are given, so what is the situation now? There's a group of individuals, some n of them. For each of them, you've got this vector specifying the ordering on some finite set, right? And now I want to infer the preference relation for the group. What kind of rules that you might use? Here is one. Prefer A over B unless 2/3 in the group prefer B over A. This is one. Instead of majority, this is about 2/3. This is actually used in some context. Every rule that I'm mentioning is used somewhere or the other. And this is a nice rule. This is completely dictatorial. There is one person in the group whose preference determines everything of the group. Our great leader. Yeah? And another one is choose the most common preference in the group. Now, I put it within quotes. There are various ways of giving meaning to it. I hope you will enjoy trying a couple of options and seeing what it means. Here is another one, minimize dissatisfaction. Okay, this is something, many social rules are not about maximizing satisfaction, but minimizing dissatisfaction, right? So minimize the number of individuals whose preference is opposite to what you decide for the group. Finally, you decide A is preferred over B. It should be that those who preferred B over A should be small in number, in the minority in general. So you can think of it as a kind of measure of dissatisfaction, and you want to minimize dissatisfaction. Now, I'm just giving a sample of a few rules like this. You can have lots of such rules, and who's to decide? Okay, So ultimately, the only way is to try out some rules of your own. Okay, it's very easy to make up rules of your own and check for what kind of properties they've got. It's a nice open-ended exploration. But remember that these rules are all ad hoc in some way. I mean, why 2/3? Huh? What is all this about minimizing dissatisfaction? Okay, so a far better way, a mathematical way, is to say this is the kind of properties I want for inferred group preference and look for ways of constructing rules that satisfy these properties. Now, what would be desirable properties? One very obvious one is what is called Pareto, after a particular social scientist. And this is in some sense, the simplest thing you can think of. What does it say? If everyone in the group prefers A over B, then so does the group, right? If every individual prefers A over B, every single individual in the group prefers A over B. You can't have a rule finally that comes out and says B over A, right? This seems like a very weak condition that you would want. Is there anybody who doesn't like this rule? Can I take it as a desired rule? Let's have how many votes? How many people think this is a desirable rule? Yes or no? No abstentions, please. Okay. So how many people think it's not desirable? Come on, I have got like 10 votes or something like that so far. One more round. Huh? How many people think this rule is desirable? So yes. Okay. How many people think it's a no? There is a huge abstention here. So one more round and I want to get a very clear opinion now. How many people vote for yes? We want this rule. There is a half hand here. Yes or no? Yes or no? Okay. Yeah. How many people say no, it is not desirable? There is one at least consistent. Yeah. I wanted to see whether people change their opinions. Yeah. So why would you not want this rule?
So basically, sometimes the preferences of a person change based on our peers. Like if the person whom you're voting in a system, like if
we just saw it, right? We just saw it. I saw people switch from no to yes. I saw yes to no. I didn't see. The 3 people who voted no are consistent at least. Yeah. Okay.
So if there is a vote for the class leader, if the person who is standing there is your friend,
okay,
and the other person is
I
not
get your
so.
point, but this is a very nice and important point. If I keep asking people repeatedly for their preferences, right, what would be stable? That's an interesting question. That's a very interesting and difficult question. I don't want to get into that. I am only looking at one-shot elections, right, where everybody casts a vote, not for just one, but gives a complete preference, right? What is the situation now? Think of it as an election where there are 5 candidates. And you are not voting for one of them, you are giving a complete preference ordering, right? You are saying, I prefer, my best is C, second is B, third is E, fourth is A, fifth is D. Give a complete ranking. That's what we are talking about, and only once. So the situation is that this vector is given to you for every individual, and you have to come up with something for the entire group. That's what we are discussing. And so this is not about repeated ones, no changing preferences. Anything else? Any other reason why you wouldn't want something like this? Not every time. This is just a one-shot thing. I have collected 140 preferences, vectors, and I want a function that takes these 140 vectors and puts out one vector. That's
but out of the 140, if 139 go for one and one goes for the other way around, you can't use this rule.
It's your rule, right? The property that I'm asking is, if it so happens that all 140 prefer A over B, the function should output A over B or B over A. That's the question. Yeah. So what we are looking at is what is the situation now? There are n individuals. Let's say there are m choices. So there is an m vector given for each individual. So there are n vectors that are there, and what you are looking for is a function that will take these m vectors and produce one m vector. That's what we are looking at. Okay, so this is one condition. Second condition is transitivity, right? Finally, the output should be in such a way that of course, if I output as vector, I'm assuming transitivity, but that's just representation. And the third one, which is commonly talked about, is independence of irrelevant alternatives. The IIA there stands for independence of irrelevant alternatives. So what does this say? This says if two profiles agree on a pair of choices. What does that mean? Here is 100, for 100 individuals, I have taken their opinion. For the same 100 individuals, there is another profile that I take. That means what? 100 vectors again. Now, in both of them, I find an agreement on some particular A and B. Right? If they agree on a pair of choices, then the group preferences derived from them. Remember, there's a function that will take for each such 100 vectors, it's going to give an assignment, right? And so in both of them, it should agree, right? So what does this mean? I have a group of individuals. Everybody in the group is saying something about A over B. But they differ on C and they differ on D. Right? My decision on A and B should not depend on whatever is the views on C and D. The other alternatives should not matter. Now, this is again something that you can debate, because my preference over X or Y might actually depend on the presence of other alternatives. Right? Now, but this is one interesting assumption. Now, this is some assumption that you might want to give up or what, and there's a lot of literature on debating whether these are the preferences you want or not. But for the moment, I want to keep these three because we can say something nice about these. And these are very simple assumptions. Transitivity is something that we began with. Pareto is a very weak assumption. And the third one really says that when you think about choosing between A and B, you are really not bothered whether there are other options around or not. The other options will matter when you want to choose over A over C or B over D or whatever, but just for this, it should not matter. This is what it says. Okay, supposing we take these and continue. And the last one is something I hope you will want. I don't know. It's a property that says there is no single individual whose preference unilaterally determines the group preference. So when is this map dictatorial? This means that it simply, there is one single individual such that out of all the 100 vectors given, it doesn't care about the remaining 99. Whatever she decides is the outcome for the entire group, right? So such a thing is dictatorial, and this property that we are looking at is the non-dictatorial derivation. Okay, so let me take these as axioms, as I said, simply because it's standard in the literature, been much debated, and something like this everybody comes up with. Now, usually this one is it's not this, there are some variants of this
Sir?
that are considered.
Here.
Where?
Down here.
Yeah.
Non-dictatorial, is it even better to put a condition like if you do the same thing, you restrict it to a subgroup or a small group of people?
Very nice,
and
yeah.
their choice also should not determine the this thing.
That would be a very interesting thing to consider, for sure, yes. Yes. But I want to start with something weak. You are looking for a stronger condition, and of course you should look for stronger conditions. But the thing about weak conditions is, hopefully if the condition is sufficient, the conditions are sufficiently weak, most people would agree on them, right? If you go for stronger conditions, there will be more disagreement among the group. So, anything else? Okay, so, very interesting person to introduce at this point, and this is Kenneth Arrow. In his PhD dissertation in 1951, this is all old stuff. He proved a very nice theorem. And the theorem says, paraphrased, if in any group of at least 3 individuals, any assignment of group preference that satisfies Pareto, transitivity, and IIA is necessarily dictatorial. Okay, so this is generally called Arrow's impossibility theorem because you want all 4, and it says that there is no function that takes in these profiles and produces one transitive relation that satisfies all the 4 properties. And I would say, one of the most influential theorems of economics. It got him the Nobel Prize in 1972, led to pretty much to the development of social choice theory, the modern social choice theory that we talk about. There's a very beautiful introduction to social choice theory by Amartya Sen, and there's a photo of Amartya Sen as well. And he got the Nobel Prize for this later. Forgot to know which year. Does somebody remember? Anyway. So Amartya Sen took Arrow's theorem further, examined these assumptions, looking at different axioms, when can you construct, etc. as well. And so I just want to go over a proof of Arrow's theorem, very simple one, and I just want to give you a sketch of how the proof proceeds to get a sense of how you can reason in such things. So in such situations, let's say a coalition G or a group G is decisive if whenever everyone prefers A over B, so does the outcome. Okay, I should really set this up all in terms of functions and talk about it, but I just want to keep it as informal as possible. Please understand the idea, and you can go and read about it and formalize it carefully. I'm going to be a bit sloppy, in fact. Okay. So, when do you say a group is decisive? The preference of that group determines the entire outcome, right? Now, clearly the set of all individuals is decisive. Why? If everyone and all prefer A over B by Pareto, that's the outcome, right? So, clearly the entire set is decisive. Now, Arrow's theorem follows then from a small lemma that we can prove. What is this contraction lemma? It says that if G is decisive, let's assume that there are at least 2. In fact, this whole thing works. For it to work, you need at least 3 individuals. Now, as long as there are 2 people, I can always partition, is what it says. You give me G, then I can find a strict subset G prime that is decisive. How does this help? Why does Arrow's theorem come immediately? Just from this, it should follow. If the contraction lemma is true, then Arrow's theorem follows. Why is that? Well, I start with any G and I keep on looking at strict subsets, right? That will give me a strict subset, and if that has at least 2, I keep going down until I get only 1, in which case it's dictatorial, right? That's it. So I just have to prove the contraction lemma. Well, how do I go about the contraction lemma? Well, G has at least 2 members. I'll partition G into G1 and G2 such that at least one of them is decisive. Well, decisive is difficult for me to get into, so I'll define something which I call almost decisive. And I'll show you how to construct a strict subset that is almost decisive. What do I mean by almost decisive? Okay, this is a stronger condition. Huh? Look at this. It says, whenever everyone in G prefers A over B, and everyone outside the group prefers B over A, then the outcome prefers A over B. Decisive says, if everybody within the group prefers A over B, that should be the decision, the outcome. Almost decisive says, if within the group everyone prefers A over B, and then outside the group, if I look at the complement, I find B over A. In such a situation, I should get, right? So, clearly every decisive group is almost decisive, because if a group is decisive, well, you can see the conditions, right? The moment I assume that everyone in the G prefers A over B and everyone outside prefers B over A, this condition is enough to give what you need. what we will show is that the converse is true as well. And therefore, it suffices to prove the contraction lemma, and where I will just show that you give me any group, I'll find a strict subgroup which is almost decisive, and then show you generally how to go from almost decisive to decisive. Okay. So what is the contraction lemma doing? It says I take G and I partition it into non-empty G1, G2. Remember, there are at least two. I can always put one in each. Right? Okay. I want to do it in such a way that one of the two is almost decisive. Well, for this, let me fix some choices A, B, C, and some profile, okay, such that over G1 we have the vector CAB, by which I mean everyone in G1 prefers C over A and A over B, and transitively C over B. And over G2 it is ABC, and outside G, that is, remember G has been partitioned into G1, G2, and there are a whole lot of people outside, it is B over C over A. This is something that I fix. Now, suppose G1 is not almost decisive. Now, not almost decisive is in the if-then form, right? That means for all A, B, if within the group everyone prefers A over B and outside the group people prefer B over A, then the outcome. Not almost decisive will say there exists a pair, right? There exists a pair such that within the group there is a preference, outside the group there is an opposite preference, and the outcome is the opposing preference. You have to get used to all these negations. So now I can use independence of irrelevant alternatives and argue that the outcome prefers B over C. Because you see within the group it's C over B, outside is B over C, throughout it's B over C. In the complement of G1, it's B over C, and that will be the outcome. Now, how did I go from a single profile to over quantification over profiles? There is some bit of jugglery involved, some careful logic has to be applied, but that's an exercise I leave to you. That's where the independence of irrelevant alternatives really gets used. Similarly, now I say suppose G2 is not almost decisive. Again, by IAA, I can argue that the outcome prefers C over A. Within the group, it's A over C, but outside here, outside G2, it's in C. G1, it's C over A, and elsewhere, it's C over A. So you will get this. So, under the assumption that G1 is not almost decisive, as well as G2 is not almost decisive, I get the outcome prefers B over C and C over A. Therefore, by transitivity, the outcome prefers B over A. But then G is decisive. If you look at G totally, right, G1 union G2, throughout it's A over B. Therefore, the group prefers A over B. So the outcome prefers B over A as well as A over B, which is a contradiction. So it's carefully set up so that, okay, so all I am saying is that you give me any G, there exists a partition G1, G2, non-empty, such that one of them is almost decisive. So now I have to prove that almost decisive is good enough, okay? So here is a proof of that. What is it that we need to show? We need to show that the strong assumption that we made can be weakened, right? So how do we do that? Well, you take a profile, whatever relation I for individual I, and given any choice x, y, if everyone in G prefers x over y, so does the outcome. Well, again, by independence of irrelevant alternatives, it suffices to show for one pair AB and a profile some Ri prime which agrees with Ri on AB that the outcome prefers this. This is exactly what IAA says. Well, consider we assume that we have at least three alternatives, right? So therefore, let C be a third alternative. Now, R prime is defined loosely like this. For A and B, do the same as R. For the group G, use A over C over B over whatever x that you have got. All other alternatives, you put them below. Outside G, you just make sure that C is the top preference, A and B come in the middle, and everything else come below. Now, G is almost decisive, so A is preferred over C. Because you can see within the group, A is preferred over C. Outside the group, it's the opposite preference, right? So, by Pareto, now you can see C is preferred over B. So, one is, since A is preferred over C, we have got. And now, by Pareto, why? Because if you look within G, you see C is preferred over B, and everywhere C is preferred over B. So all individuals prefer C over B, and therefore the outcome prefers C over B. Now, by transitivity, A is preferred over B, which is what we needed to prove. Okay, this is like major sleight of hand. I mean, somebody just down, boom, 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 and says in a loud voice, of course it must be true, right? So, no way can you understand proofs like this. Huh? I mean, somebody says, there's no way you can understand proofs. But this proof is so simple, so very simple, that you can do it, right? So, you can sit, take the definitions, pull them apart, write down things, set it up, and do it. It's absolutely straightforward. The real trick is only in understanding the structure of the proof. Once you understand the structure of the proof, the details follow very nicely, but you have to be very careful with all the quantifications that we are using. Okay, so I just wanted to tell you that Arrow's theorem is remarkably simple, very elegant, and very general. And you can show that what seem like very reasonable assumptions, if you put together, there is no decent aggregation function. There is nothing, there is no function that takes individual preferences and computes a social preference that satisfies very simple properties. Now, of course, that inaugurates a whole industry. Like I said, people have looked at various kinds of, you can say, by the way, you should also show that these assumptions are independent, these axioms are independent. How do you prove that these axioms are independent? By showing that if I take any combination of the other three, it doesn't necessarily imply the fourth. And you can construct functions of that kind. Okay, so I want to move on to a second topic within the same thing, a particular thing where I am not really interested in preferences, but I want to come up with decisions. And that is true of elections. Right? Elections are also about aggregating social preferences from individual preferences, right? Let's say the alternatives that we are looking at are not laptops and such things, but there are people, M candidates standing for elections. Each of us has a complete total order of preference on the candidates. Again, it's not reasonable to say that you must actually prefer somebody over the other. Mostly you don't care. But let's assume again that for each voter, you are given a complete preference. You go to the voting booth and you don't just tick one, but you give a complete ranking of all the candidates. Let's assume that you've got the votes from all the voters. Somehow now you have to declare who is the winner, who wins, right? So you're looking for a function that will take into account, if there are n voters, you have got the n vectors, and out of them, you have to declare somebody as the winner. Now, what kind of mathematical properties that you can look for? And this is a research that was started in the 18th century by Condorcet and later by Borda. And 19th century, this Charles Dodson. Is this name familiar? Does anyone know Charles Dodson? You all know, so under a different name. So, how many people know Lewis Carroll? Alice in Wonderland. That's Lewis Carroll. So, Lewis Carroll is the pen name of the mathematician Charles Dodson. He did a lot of very, very interesting things. One of the things that he was quite a maverick, wrote about many different kind of things, and one of the things that he wrote about were electoral systems. In particular, this election function is something that he talked about. And then Kenneth Arrow, and after the Arrow's impossibility theorem, this thing became very important. I'll also mention Satterthwaite's theorem later. And here is, I think, Marquis de Condorcet. And Condorcet, of course, there were no photos. Okay, so this is all some paintings from somewhere. And yeah, can we distribute? Yeah, sure. Yeah, please. Yeah, so here is an example that we'll make use of in the next 15-20 minutes. So there is one sheet for 2 people, so yeah. So it's the same thing printed twice, so tear and pass to your neighbor, right? 2, yeah. So one sheet for 2 people, yeah. Halve it and pass to your neighbor. And while you're doing that, here is another picture. This is Jean-Charles de Borda. And both were 18th century mathematicians who were sitting and worrying about how to conduct elections. I don't even know if the kind of general elections we have existed in the 18th century. So these people were far ahead of their times. Hey, Ananta, what about upstairs? Or will you? Okay, so what are good rules for elections? Well, we all know first past the post, right? In all our elections, you calculate, everybody votes for someone, you calculate the votes, whoever gets the maximum is declared the winner. This is what is called first past the post. Now here are some famous what are called one-round elections. Plurality. Each voter awards 1 point to her top alternative, and the one with the most points wins. This is the one used in almost all political elections all over the world, right? So basically, instead of, when you go and vote for only one person, think of it as a vector where you are giving 1 to some particular candidate and 0 to the rest, right? So this is the special case. Okay, and Borda count is very interesting. This is what Borda suggested. You saw a picture of him earlier. He suggested, suppose we have m alternatives. Just listen. Huh? So suppose you have 5 alternatives. Then, and my ranking is A, B, C, D, E. That means what? I give 4 votes to A, 3 votes to B, 2 votes to C, 1 vote to D, and 0 vote to the last. So each voter awards m minus k points to, his kth ranked alternative. And the one with the most points wins. And this is used, for instance, in the national elections of Slovenia. Every rule I'm talking about is used somewhere or the other in the world. I may not have put it in, but okay. There is the veto rule. And veto rule is extremely interesting. This is also used in some parts of the world. This says, for each alternative, count the last place votes, and the ones with the least of them wins. Right? Among those who are ranked lowest by everybody, knock them off. Right? The ones who are hated least in society win. This is also used in some place. Okay, now I have given you this sheet. What does this mean here? If you look at your table there are 100 voters, and I have given you 100 vectors. Rather than giving 100 vectors, I tell you 33 voters prefer, what is the ranking they give? A, B, C, D, E. Then there are 16 voters who have given the ranking as B, D, C, E, A, right? Now, so you've got, these are the voters. First question says, by plurality, who wins? Why is that? Maximum number of people have voted top for A, right? So by first past the post, A wins. Is this clear? Is it clear to everybody that by plurality A wins? Okay. Now let's do the Borda count. This is going to take some time. What is the Borda count for A? Yeah, sorry? Somebody? It's not easy. Let's start. Very good. For the others, those who have not yet understood, let me just do it a little slowly. 33 people have given 4 votes for A. Is that clear? If you look at the first list, 33 people have ranked top. So 33 times 4 is where you get that. And then the next 16 gives 0, so no thing. And then next 3 of them give 1. So 33 times 4 plus 3 times 1, and then rest is all 0. So as far as A is concerned, it's 33 times 4 plus 3 times 1, and that is 135. So A's Borda count is 135. Now let's look at B. How much is it? 247 or 37? Oh, okay, let's see. I want to wait for it. So start counting. 33 people give vote of 3 to B. Why are people sitting quietly? Why are you not calculating? Of course you should be, no? You got the table, you got the thing, just do it. Come on. So 33 people are giving a vote of 3 to B. I'll wait for some majority answer, yeah? What about the next 16? They give a vote of 4, and then the next 3 give a vote of 3. Next 8 give a vote of 3. Next 18 give a vote of 1. Yeah, 3, 2, 1. Yeah. So, what have you got? Borda count for B. Shall we move? So, yeah? What happened to your numbers? Have you got? Yeah, 247 is the thing you should be getting. What about Borda count for C? 244. Yeah. Okay. So anyone has already gone to Borda count for D? (33 times 1 plus 16 times 3, 3 times 3, 8 times 1, 18 times 4, 22 times 1. You have to add all of these. Okay. And then the rest have to be less. Come on. E has to be less. Yeah. Yeah. So who is the winner according to Borda count? B. The numbers are set up in such a way that B comes out as the Borda count winner. Okay. So notice that we have not changed the preferences. It's the same preferences. If you use plurality, A comes out as winner. If you use Borda count, B comes out as winner. Veto I'm not going to do now. Let's move on. Now, the elections that we saw were single rounds. There are also multiple rounds. For instance, This is something that is much debated these days. Actually, if you go now, look at political science, one of the biggest discussions is about this STV elections. This is called a single transferable vote. And this has m-1 rounds. For example, for this, there will be 4 rounds. What do? In each round, look at the ones getting smallest number of votes. And that one is eliminated. And then look at who is surviving. And basically now you have to transfer all the votes for the least one to the next above. Compute, again eliminate the least one, keep going up. Of course, after m-1 rounds, there will be one winner, and that one is declared as winner. And this is a system that's actually used in Ireland, Malta, Australia, and New Zealand right now. It's a more complicated one, but of course, once you have electronic voting, it's quite easy to implement. Okay? And then there is something called plurality with runoff. This is a 2-round election. In the first round, 2 alternatives with highest plurality votes survive. In the second round, the winner of a pairwise election between these 2 alternatives becomes the final winner. This is what is used in the French elections. Recently, French presidential elections, if you saw, there was no clear majority at all. Macron and Marine Le Pen came out as thing. And even though, well, and then there was the second round where Macron won the elections. Then again in the French assembly elections, similar thing was happening. They predicted that Macron would win, I think 450 seats out of 520. Actually, Macron's party won only about 380 or so later. So this second round between the top place can actually make a big change. So here, for this thing that I have given you, who are the top people? Who are the top 2 in plurality? We already said A wins. But actually, if you look at the top 2, who is it? A and E. Now, if you do one-off election between A and E, who wins? Now let's have notice that first round, A and E are the top placed. Now if you have a pairwise election between A and E, who wins? Take a look. Is it clear that E wins? Yeah, so why don't you enter that? The last one, plurality with runoff, gives you E. Okay, single transferable vote I will not do for now. Let me just move on. Then there is this very interesting thing due to Condorcet. In fact, Condorcet was the one who really began this whole business. So Condorcet's suggestion is this: conduct pairwise elections, and the winner is one who beats every other alternative in a pairwise election. So all this business of, you've got the complete vectors, but you must look at how A would fare against B, A would fare against C, against D, and so on. Here. So take a look at this, and let's do pairwise election. Yeah. Consider A versus B, A versus C, and so on. Yeah, go on. Who is the winner? In general, you need not have a Condorcet winner. How do you prove that you need not have? You must give a counterexample, right? We already looked at majority, right? Look at the preference that I talked about right in the beginning. With 3 people, it's easy to show that there is no Condorcet winner, right? Pairwise, A beats B, B beats C, but A doesn't beat C. So in general, you need not have a Condorcet winner, but in this one, there is a Condorcet winner. The numbers have been set up in such a way that there is a Condorcet winner. So, can somebody guess? You all prepare for exams, no? How do you guess your answer when you don't know the answer? Come on. I have given 5 choices, and I have written 1, 2, 3, 4, 5. The first answer was A, the second answer was B, the last answer is E. Come on. Yeah? The Condorcet winner is C, obviously. Yeah. So you can. Okay, I'm not going to take too much time on this. Please sit and verify that the Condorcet winner is C, and the single transferable vote is much harder because now you have to conduct 4 rounds of elections, each time transferring the vote, and you will see that the winner is D. So, what is the moral of the story here? This table tells you that depending on the winner, whom you want to win, you can pick your rule, right? So, there is no sanctity to which rule, and all these rules are used somewhere in the world, right? Okay, so there is this notion of Condorcet consistency. I'm going to skip that. There are more rules. I just wanted to mention the Dodson rule also. There are very interesting rules. These are some sample of rules. I have not got into the axiomatic treatment of this, about what kind of desirable properties you have, you might want, and look for electoral rules that achieve these properties. But all of them have interesting consistency properties. And some of these rules are complex, and the winners are actually hard to compute. Now, there are some very nice mathematical ways of saying which is easy to compute, which is hard to compute. For instance, if the number of steps needed to compute the winner is polynomial in the size of the input, you tend to consider that as easy to compute. Now, Dodson winner is hard, and we believe there is no easy answer to these. And a lot of very interesting work is going on what kind of electoral rules are good, what kind of restrictions you can place on preference relations, all this kind of stuff. I also want to mention a very important topic in this area, which I am not getting into, but worth looking at, and this is about manipulability. We say that a rule is manipulable if there exists a profile where a voter I can switch her preference from Ri to Ri prime. Let's say my actual preference is this vector A, B, C, D, E. But I falsely go and register A, B, D, C, E, just so that by doing that, the result swings from, let's say, B being the winner to A being the winner, right? So then you call that rule a manipulable rule. And there is a beautiful theorem of Gibbard and Satterthwaite, which says that if a voting rule has at least 3 possible outcomes and is non-manipulable, then it is dictatorial, right? Again, yet another impossibility theorem. In this area, that is the fashion. If you can prove some particular impossibility theorem, you are famous, right? And they didn't get the Nobel Prize, but they've got other prizes. So, and what is very interesting is that the same complexity that I mentioned comes to the rescue at this point. We can show that, yeah, that's manipulable, but manipulation is really hard. That somebody who's trying to manipulate needs to compute something that takes exponential time, right? So you need enormous amount of resources to be able to manipulate elections for many rules. So rules which are complex in terms of declaring winners are actually very good in terms of being resistant to manipulation. Now, when can you do what and so on? There is a beautiful theory that is being developed. A lot of work is going on in the last 25 years or so on this. So this is a very rich field of intellectual endeavor that intersects philosophy, politics, economics, uses tools from, I'm just going to conclude, so let me, mathematics and computer science. I would say that the moral of the story is that societies cannot be rigid about rules like this, which are important for democracy. Social preferences are hard to derive, and the logical difficulties in doing so need to be acknowledged and addressed, rather than pushing them under the carpet, so to speak. And with the advent of the internet and algorithms that make decisions, that make choices, these considerations apply to a far wider variety of contexts today than before. This is not just about elections, it's in general about aggregating preferences, and for instance, on e-trading and internet e-commerce and so on, there's a lot of applications of these as well. And committee voting, for instance. So there is a lot more that's happening here. I just want to introduce to you a very interesting area where social choice theory in general is an interesting subject because it brings together considerations from a wide variety of fields, very simple mathematics, and leads to a lot of fairly complicated logical considerations. I'll stop here. Thank you. Yeah, sorry, Sushmita. You want to say.
So you said that manipulation is NP hard. So how do you frame a manipulation problem? It also you need to know what everybody else is going to do, right?
Right. Okay. So that's because I assumed that the setup was complete with everything given, all the, it's all total, all that. It need not be in general, right? So in general, you want to ask, with what small subset of knowledge or preferences can you already manipulate? Of course. Yeah. But then it's all very complicated. So I just presented a very simple version of that. Yeah. Other questions?
Any other questions?
Not any other questions. Yeah. Well, if you don't have questions, I have assignments to give you. So.
Is there some sense of measure that you give to compare two kind of election system based on, if I give you a certain characteristic of your population, not exactly telling you what they are preferring, then the election is done. If you want to decide it on previous hand, the election is going to happen after some time, and the characteristic of your population is known. You more or less assume that your population is distributed in such a way, and you want to kind of manipulate. You have the power or something, and you gets to decide the election process. Can you do in some sort of way that manipulate this process and increase the probability of your winning choices or something?
It's a very good question. I mean, I gave everything in the deterministic thing. Again, because I want to give a 1-hour talk and just give the outline, right? Almost none of these things make sense as I have given. Probabilities are a much better way of doing this whole business. Okay, so preferences are given with probabilities. This is one thing. And in general, they are also incomplete. Okay, so what is very nice then is exactly as he said, you can start looking at distributions. You can start, if you know statistics, there are a whole lot of statistical inference you can start making from these, right? So you can start looking at trends, you can start looking at overall this. What you cannot get from these are electoral rules. Remember, electoral rules are very different. They want to declare one person as the winner, right? So what you can talk about, you can try to use these kind of analysis to say that, given a particular rule, A is more likely to win than B. That's about all you can do. The question that was asked about the existence of an aggregation function or the existence of an electoral rule still remains. The negative theorems, impossibility theorems all apply. You can't escape that. So what you can try to do is to give up one of the conditions and try to look for some compromise within that. That's about all you can do. But almost all, it doesn't matter what setup you take, because the thing is formulated in terms of existence of a function satisfying these properties, that will remain. But it's certainly true that the information available to you will be in general probabilistic.
Good evening, sir. My question is there any objective ways to prefer one system to over another? For example, we have, as for now, we have seen 5 systems. Are there any objective ways to...
That's the answer. You cannot be, there is no, I don't know what objective you mean here. The theorem very clearly says that, right? Or even the numerics tell you that for the same profile, if you choose this rule, A is the winner, and if you choose that rule, B is the winner, right? So the point is, it is the society which has to decide which they consider to be the most reasonable rule for that society.
So how do we decide whether it's reasonable or not?
Well, I would say by looking at the properties that that particular rule has, right? So some rules have Condorcet consistency, some rules don't have Condorcet consistency. So I would say looking at the axiomatic basis of these and say whether, axioms are those you accept or reject, right? So this is the point. So I would say I like axioms 1, 2, 3, but not 4. Another society, another group says, I like 2, 3, 4, but not 5, etc.
So as for now, it's completely arbitrary for choosing one system.
It's not entirely arbitrary. It's, as I said, which you consider reasonable and which you consider unreasonable, right? The theorem is very clear that if you wanted all of them, there is no solution. You have to give up something. So it depends on choose your poison, as they say, right? Yeah.
Actually, it relates to his question. If you can somehow characterize the nature of the society that you're looking at, for example, a very diverse one, or is there some method that because you mentioned that different systems.
There's a lot of literature in political science on these issues. I don't know enough to, give a quick answer, but scholars have been writing a lot about what can you read about societies based on the preferences they have for, saying that I choose to keep Pareto and IIA, but I do not want transitivity. What does it say of a society? I don't know. I'm saying that you leave to philosophers and political scientists, and they do discuss these things at some length. I'm not sure mathematics can provide good answers to them. My point is that the right answers for those things are somewhere else, right? It's about acceptance or rejection of certain axioms. The mathematical considerations start with, okay, with these axioms, this is what happens. Impossibility theorems point out to certain things being too strong, that's all. Yeah?
So the US presidential election does not fit into any one of this. So are there any more methods which you have just skipped or something?
It's a first past the post. It's a direct first past the post election. It's a plurality, straight. There is no ambiguity at all. It's a one-round plurality-based election. You're probably thinking about primaries and so on. That is party stuff.
No,
The presidential election is nothing to do with, finally the party candidates are decided by some process, right? That's a separate thing.
Yeah, because in the recent election, there was a criticism, like there were some people who were supporting Bernie Sanders over Hillary Clinton and all this thing.
Yeah.
So they felt that system was bad.
No, but once again, you are talking about something within the Republican Party or within the Democratic Party, right?
Yeah.
That has nothing to do with the final election, which is between certain individuals.
So you look at it as only a plurality between two people.
Yes, that's what it is.
Okay.
That's what it
You
is.
don't count the previous rounds.
That's what it is. Because notice that each party has its own way of electing its candidate.
Yes, that is there.
And you can question that. And that one again is plurality.
Yes.
Right? So that's the problem.
Okay.
If, for instance, you can look at the Indian presidential elections, right?
They have
There is an
multiple
electoral
values.
college. I don't know how many people understand the electoral college of the Indian presidential election, right? Where do you get these numbers of 1,52,000 votes, etc., right? So all this comes into. Yeah.
But in the Indian presidential election, it's a proportional representation, but it is single transferable.
Correct. It's an STV. I've already talked about that. That's a little. The only thing is that STV is not computed in multiple rounds. So there is a direct formula that has been employed in the Indian Constitution. There are many variants of all these rules. I have only presented a few kind of famous rules. There are many more complicated variants of all of these, which of course are harder to analyze.
Sir, but the US elections, it is not completely plurality, no, sir. They have this electoral system where certain states have more electorals.
Oh, that is about finally the number of, okay. Now is that what you were saying? Okay, now I understand what you are saying, is that, yeah, you are right. It's about each state uses plurality, right? Who wins the state is by plurality. After that, the number of seats or votes that points, whatever you can call them, that each state contributes is added and you take the total. That's correct. But within each state, it's plurality. So, I mean, it's not any of this multi-round election or anything of that kind. It's just a one-shot. Anything else? Okay, I think I should.
Okay, let's thank the speaker.